All right, let's talk about the fundamental theorem of group homomorphisms. So, FToGH. So, I'm going to let phi be a homomorphism, a group homomorphism between two groups G and G prime. Let pi from G to G mod the kernel. Actually, no. Before we do this, let's just, to make our notation a little nicer, let K be the kernel of phi, and pi from G to G mod K, the natural map, i.e. the projection map, i.e. you send an element of G to the coset GK. I'm going to write this K a little nicer, and the other one could be nicer too, but I don't really care about that one. Okay, so then there exists some phi bar, which is a homomorphism from G mod K to G prime, such that the following commutes. Okay, so we're going to draw a picture. So this is nice. It's not quite like an analysis where the pictures are like space and you can actually kind of see what's going on. But this actually sort of gives you a little bit of an idea of what the structures that's going on is like, and so it's not super bad of a picture. It's nice. So we have these maps. So this is pi, and this is I. So this is the inclusion map, because the image of phi is a subgroup of G prime. And so what we're just doing is we're just considering the inclusion map that will send. Does this even make sense? No. Oh, I did it again. I feel like these should be flipped. Because what happened? Okay, so this is going to be phi. Well, let's see here. Phi is a map from G to G prime. Oh, of course. Okay, so yeah. So phi is going to be a map from G to G prime, but when we actually sort of map through here, we're not starting at G prime. Yeah, I guess this map, I don't really quite like this map because it's not defined on all elements of G prime. But if we're considering this as like a commutative, oh, by the way, I should write in the rest. But anyways, if we're considering this as a commutative diagram, then what we're doing is we're starting here, and then we're moving through the diagram. And so what happens is when we get to G prime, the only things that are going to get here are things that were sent here by G under phi. And so the only things that are going to end up here are things in the image of phi. And so that's why this is a well-defined map. It's because it's actually a map from, yeah, I don't know. I've seen this proof presented in different ways, but this seems to work well enough. Also, phi is an isomorphism. And that's really important. Typically the way that you might see this is, so this projection map is injective. You prove that, let's see here, psi, we're going to prove that psi is surjective. And so a lot of times what you'll see is you kind of won't see this part here. You'll kind of just, if that's the part we're not seeing, I don't know why I circled that instead of circling the part that we are seeing, which I guess makes a little more sense, but whatever. So typically what you'll see is you'll see this, G, G prime, and G mod K, and so this will be injective and this will be surjective, and if G prime is, and if this map is surjective, if phi is surjective, then this, if we're going through here, yeah, if this is surjective, then psi is going to be an isomorphism. And it turns out if this is surjective, then we can just replace G prime with the image of phi, and then you're basically just, it just becomes like you take this and you put it here, if that makes sense. So yeah, this isn't super neat and everything, but it'll do the job. And oh, by the way, the diagram commuting means that if you start here and you go this way, that'll be the same thing as if you start here and go this way, and it's also going to be the same if you just do like squiggly like that, like if you go this way. You'll end at the same place. You'll end at the same element. So I wrote prop when I should have wrote proof. So anyways, let's prove this. To find psi, oh, of course this is a little confusing because I haven't written it up there. So we're going to find it here, psi from G mod K to G prime by psi of GK equals phi of G. So you plug in a coset and you get phi evaluated at a representative of this coset. So the first thing that should jump out at you is that we have to check that this is a well-defined map. So for well-definedness, let G1 K equal G2K, i.e. suppose that G1 and G2 are two representatives of the same coset. Then, what does that mean? We know that this is equivalent to saying that G1 inverse G2 is an element of K. So, what happens when we evaluate phi here? Phi of G1 inverse G2, well, this is in K, and K is the kernel, so phi is going to send this to the identity E prime. Okay, since phi is a homomorphism, we can factor the phi through, well, not factor, but you can break up this product and bring the multiplication in here to multiplication outside, like so. Phi G1 inverse phi G2 is equal to E prime. And so we multiply on the left by phi G1, and what we're going to get is we're going to get phi G2 equals phi G1. So in fact, this is well defined, because when you plug in psi of G1K and psi of G2K, we're going to get phi G1 and phi G2, and these are the same. By the way, the difference between phi and phi, I don't know what exactly the difference is, but I think it has something to do with, like, if there's a vowel before the phi, then it's a phi. It's some Greek alphabet stuff that's not important for proving the fundamental theorem of group homomorphisms. So let's get back to this. Let's see here. So what do we want to prove now? Psi is a homomorphism. Basically, I'm just going to, instead of taking up the space to say like, oh, I'm going to prove this, and this, I'm just going to prove a whole bunch of stuff. So psi is a homomorphism because psi of G1k times G2k, this is going to be equal to psi of, remember how multiplication works. With cosets, you just multiply the two elements together. And then, well, we know what this is. This is phi of G1, G2. But phi is a homomorphism, so this is phi G1, phi G2. And then this, of course, we can convert back to psi. And this is psi G1k, psi G2k. See here. Psi is injective because psi of gk is going to be equal to e prime if and only if phi of g is equal to e prime, but that happens if and only if g is in the kernel, i.e. g is in k, and if g is in the kernel, it's if and only if gk equals k. So the zero element is the only thing that goes to e prime. And here the zero element is the whole subgroup k, because it's the kernel. So gk equals k. Okay, so psi is an injective map. And now phi bar is the same thing. Do we actually say what phi bar is anywhere here? No, we don't. But what this is this is the inclusion map, so we're restricting G prime to the image of phi. And so phi bar is just going to be the same thing as psi, but instead of mapping into all of G prime, we're only mapping into the image of phi. So we know that phi bar is an injective homomorphism because psi is, and also phi bar is surjective. That's because if we think about what the image of psi is psi of gk equals phi of g. And so the image of psi is going to be exactly the image of phi, because anything that's in the image of phi, you get there by evaluating phi at some element g, and then if you take psi of gk, then you'll get that same thing. And so psi maps, so psi will hit everything in the image of phi. And so if we take psi and we restrict where we're mapping psi, we restrict it to the image of phi, then it's going to be surjective because it's going to hit everything. And so phi bar is a homomorphism, it's injective and surjective, hence phi bar is an isomorphism. Now, it turns out that phi bar is, I think it's both phi bar and psi end up being unique. There is a uniqueness statement that typically goes with this, and it's not really hard to prove that part because you sort of show that this is the only way you could define such a homomorphism. But of course, like, you need to put in a little more work to prove it, but we're not going to prove that here. We're just going to stick with this theorem. So if there's any parts of this proof that look a little confusing, or this looks like some of the things have been presented in sort of a way that doesn't make a lot of sense to you. For example, if you're uncomfortable with this I here being this inclusion, where the way their inclusion should really be going is you should consider the image as the image of phi is included in G prime. But anyways, this is a pretty standard theorem. Most algebra textbooks, whether it's like a first course in algebra or like a more advanced algebra course that's just kind of like assuming that you've seen it already and going a little more depth into stuff, they'll all cover this because this is fundamental. That's why we call it the fundamental theorem of group homomorphisms. So you can always just just grab a textbook, grab Artin, grab Dumton and Foote, grab Jacobson, Basic Algebra 1, grab any textbook and you'll be able to find a proof of this. And if you look around and you find a bunch of proofs that you don't like, then eventually you'll find a proof that you like. But I don't think there's too many ways to prove this. You just have to. This is a type of proof that you see a lot of in algebra, where the theorem statement is harder than the proof. Yeah, I guess it's not super. Like there's some things in algebra where there's a trick, and if you don't have the trick, you can't do the problem. This is not like that. The trick is knowing what the right theorem statement is, and then proving is you just check a whole bunch of things. But anyways, I'll stop rambling about this, and next time we'll move on from here.